In this problem, we have a rotating table that has a disc on top of it, and this disc is connected to the middle of the table with a cord. And we're given that the max tension that this cord can withstand before breaking is 100 newtons. So we're asked to determine when does the cord break, and we are given that the mass of this disc is 3 kilograms. The initial velocity is 0 meters per second, and the coefficient of kinetic friction is 0.1. So if we start with our free body diagram, we're actually going to have 3 dimensions this time. We are going to have this B or binormal direction. We are going to have this T direction, which is our tangential direction, and we are going to have our normal direction. And if we draw our disc, sort of try to place it, the middle of it to the origin, we're going to have a force coming down, and this force coming down is going to be its mass times gravity, so it's going to be 3g, and we know gravity is going to be equal to 9.81 meters per second squared because we're in SI units. And we're going to have a force NA, or I guess we can call it ND for the normal force of the disc, that this table exerts back on this disc. And there's one more force we have to put in, and that's this frictional force. So if this table is moving this direction, the relative motion of this disc with respect to the table, it looks like this disc. So the table, if the table thinks it's still, it looks like the disc is moving this way relative to the table, right? So the table is moving this way, and if we pretend the table's not moving, and how does this disc look? This motion of the disc with respect to this platform look, it looks like it's moving in this direction. And so that's what our frictional force opposes. It opposes the movement in this direction. So I'm going to draw it like this. So this is our frictional force. And our frictional force we know is mu k times the normal force. And this last force we need to account for is in this normal direction, and that's not a great color. It's this tension of this rope that's holding this cord to the middle of this platform. So we'll have a T, and we can equal this to a kinetic diagram, and when we do that, we have an acceleration, a mass times an acceleration in this tangential direction. So m times our m, which is 3, times an acceleration in the tangential direction. And in the normal direction, we're going to have a mass, which is 3, times an acceleration in the normal direction. And if you notice, this binormal direction has no acceleration in it. So what that means is this sum of the forces in this binormal direction is going to be equal to 0. And if we sum our forces in this direction, we have minus 3 times gravity is equal plus our normal force of the disk is equal to 0. So our normal force of the disk is equal to 3 times gravity, or 29.43 newtons. So that's good, because we need that ND when we sum our forces in our tangential direction. So let's do that. If we sum our forces in this tangential direction, we get the sum of the forces in the tangential direction is equal to a mass times an acceleration in the tangential direction. So the sum of the forces, if we do this, it's mu k times nd is equal to a mass, which is 3, times this acceleration of the tangential direction, and this at is equal to this 0.1 times 29.43 divided by 3, or this is equal to 0.981 meters per second squared. So the last thing we have to do is sum our forces in our normal direction. And this is equal to the mass times the acceleration in the normal direction. So if we sum our forces in the normal direction, we have this t right here, and this is equal to our mass, which is 3, times our acceleration in the normal direction, which is an. And this gives us that 3 is equal to an. However, an is equal to a velocity squared divided by a radius of curvature, and we want to solve for this v squared. So we know that if we substitute this in for an, we know that our tension is equal to 3 times a velocity squared over the radius of curvature. And if we're figuring out the velocity when this breaks, let's look for the velocity when this breaks. We have 100, which is the critical tension, is equal to 3 times a velocity squared divided by a radius of curvature, which is this 1 meter right here. And we can solve this, and for our velocity, for this critical velocity, we have a critical velocity which is equal to the square root of 100 divided by 3, and this is equal to 5.77 meters per second squared. So the critical velocity when this rope breaks is, it's not meters per second squared, it's just meters per second, is 5.77 meters per second. So at what point does this cord break? If we know our final velocity is 5.77 meters per second, we know our initial velocity is 0, we can use this equation v equals v naught plus at. And we know our acceleration. Our tangential is, we're going to use our tangential acceleration, and that is 0.981 times some t, and we can solve for t, and we get 5.88 seconds. So what does this tell us? This tells us that starting from rest, when this platform begins to rotate, it takes 5.88 seconds before the tension on this cord is 100 newtons, and when this tension on this cord is 100 newtons, this cord will break.